The demand estimation part of the design project should be uploaded by 1 o'clock on Monday. And of course, the purpose of having a draft submission is so that I can give you feedback and you can make adjustments before the final submission of the project report, which is sometime in April. Now, don't have the wrong idea that because this is like your first submission that it's okay for it to be incomplete. We talked about last time how it needs to begin with that summary table, should include accompanying calculations that shows how you determined each of the flow rates in every cell of that summary table, and then also the written description of your assumptions and research. And so I'd say that phase 1 of the project is probably the one that takes the most time. And I think overall, just to give you an idea, I think that you could probably do a great job on the project in 20-25 hours. And my past experience suggests that maybe students spend probably 5 to 7 hours on the demand estimation. So that's due on Monday, and then I'll take next week and spring break week to be looking over it and giving you feedback that you can adjust before you finalize your pipe sizing. Because of course, the pipe sizing that you do in phase 2 depends on the flow rates. And so you need to have a good idea of what flow rates ought to go into WaterCAD when you're sizing the pipes. The next thing beyond design project phase 1 is homework 8, and that's due a week from today. It's posted on Blackboard right now. It's available. It's different problems that the thing they have in common is that you need to use Manning's equation. So for steady uniform flow, that is the depth that you determine with Manning's equation. We've got a few more examples today that we'll get some additional practice solving for the depth in the trapezoidal channel, just so that you're nice and good at that. So we're still in chapter 12 of the book, moving on to sections 4 through 6. Any questions related to the announcements or anything you want to ask about for the design project before we get into this discussion on channel efficiency? Okay. Well, let me know if you've got questions on the project as you work through the weekend. If things come to mind, you want to check with me, you can call me on Teams or send a message via email. Here's a picture of a channel that's kind of in rough shape. You can see that there's been some scour, that a lot of land has been moved downstream when the rain floods. When the rain is falling hard, then it sends a big stream event through this channel, and then the erosive force of the water as it moves downstream is taking soil and rocks and sediment along with it. So this is just an illustration that the soil sometimes doesn't have the internal strength to resist the scouring effect of the water. And we can calculate the magnitude of shear stress that's applied by the water onto the surface if we know the slope of the channel, we know the hydraulic radius of the channel, and the unit weight of the water. So this would be the shear stress that's applied to the soil, and geotechnical analysis can tell you what shear stress can be resisted. And so there are tests where they're pressing on the soil with a certain force, and they know the area of the column of soil that the shear force is being applied, and then they can detect when the soil begins to move. So Manning's equation can be used to find the maximum velocity that should be allowable. So if you know, for example, the slope of a channel, and your geotechnical analysis defined the maximum shear stress that can be applied, and of course for water the unit weight would be 9810. You'll calculate some hydraulic radius. And hydraulic radius in this example, the way that we're going to use it here, is just kind of an intermediate. It doesn't necessarily have physical significance. it doesn't necessarily mean that this channel has that hydraulic radius. It's just the corresponding hydraulic radius that would be in equilibrium between the shear stress that's applied for a certain slope. And so once you have that hydraulic radius calculated, if you rearrange this equation and solve in terms of R, then you'd put it into Manning's equation. And so remember that we already know the slope, and we could look up the roughness factor depending on what the channel is made out of, and then you'd find what velocity is the maximum velocity that's going to cause that shear stress. So that's kind of the thinking behind this example. If we've done a geotechnical analysis and we know that the maximum permissible unit tractive force is 10 newtons per meter squared. So that's just an idea of, if we have this channel and the water is moving downstream, that of course the soil is resisting that flow. And so the water is moving downstream, the soil is resisting the movement of the water, but eventually the scour effects of the water are going to be enough that it can begin to cause the scour and erosion of the stream bed. And so the internal strength of the soil here, 10 newtons per meter squared, is what we've got. And we want to find out what velocity, in terms of meters per second, is the maximum allowed that would limit this erosion in the case like this, where we know the slope is going to be 1.5%. And just to remind you, when we use Manning's equation, S should be expressed as a decimal, not as the percentage. And so here the value that you will put into S, both here and also in the expression for shear stress, is 0.015. And then if this happened to be a natural earth that was in good condition and the channel is straight, then the N value you should use is 0.02. All right, so I'm going to pause for a moment where you calculate the velocity, the maximum velocity that can be allowed. And the way that you do it is, first of all, rearrange this shear stress equation, solve for R, and then substitute that R into Manning's equation. These are pretty typical values here. 10 newtons per meter squared is a pretty middle of the road tractive force that could be permitted by a soil, and a 1.5% slope is pretty typical for a relatively small stream. By the time they get much bigger, they usually flatten out. Like the Ohio River isn't 1.5% slope, it's much flatter than that. A typical N value. So if we calculate all of that, what it tells us is that up to 1.02 meters per second, the water movement isn't going to be scouring the soil. But then beyond that, it's going to begin to erode and move sediment downstream. 1.02 meters per second, that's about 3 feet per second. So, it's not moving too swiftly there, but yeah, pretty relatively simple approach. Any questions about this example before we move on? Now, some of the ways that we can actually physically measure velocity, there are tools that you can dip the water, dip a pole down into the water, and you can see that there's an impeller at the end of this that will begin rotating, and then the speed of its rotation is calibrated to the velocity of the water that it's immersed in. And then here at the top is a little display that has calibrated the number of rotations per minute to the velocity of the water. So this is one way to find out what the water velocity is, but the water velocity changes as a function of depth. The velocity may be relatively fast moving up at the surface where there's not resistance, and slow moving down beneath. And there's a couple of different formulas our book introduced for calculating and estimating the velocity distribution. So this velocity profile, where the further away you get from the bottom of the channel, the velocity increases. This formula is in the book, and it utilizes what's known as von Karman constant, and you can see that the depth y, the distance from the bottom of the channel, is compared to the overall depth of flow. And so that's one approach. The simpler suggestion that our book has is that it's just typically the velocity at a depth of about 4/10 of the way from the bottom of the channel is typically about the average velocity. Or another approach is to measure the velocity 2/10 of the way up from the bottom and the velocity 80% up from the bottom, and then that might be a way to find the average velocity. And by definition, what we mean by average velocity is the volumetric flow rate divided by the area. But we don't always know what the volumetric flow rate is. Often what we would do is we would determine the volumetric flow rate by multiplying the average velocity by the area. So this is just suggesting a couple of different ways to determine what is the average velocity. You'd take a sensor like this, and if you knew that the channel is 2 meters, then you'd measure it 2/10 of the way from the bottom, so 40 centimeters off the bottom, and then you'd meet at 80% depth, you'd measure it, and you'd find the average velocity that way. Another thing that our book addresses in this section, in chapter 11, is the fact that you'll often have a different roughness value in different sections of the channel. So what we're looking at here, this is the main part of the channel, the main channel that the water would be in when there's relatively low flow rates. But when there's flooding, a real excess of water, then the water levels will rise and water gets out into the floodplain. And there's different things in the floodplain than there is in the main channel. The main channel may be concrete lined, or it could be a smooth soil or a packed clay. But in the floodplain, there's all sorts of debris. Just to illustrate, let me show you a video that I made a couple of years ago. Let's see, when was this? Almost exactly a year ago. So this was March 30th, 2021. And what we're looking at is Harris Riverfront Park here in Huntington. And so like this is the movie theaters at Pullman Plaza, if you're familiar. Let me maximize this. This is the movie theaters at Pullman Plaza. Here's the Red Cross building. Here's the flood wall. So you can see that the water levels were a bit higher than usual a year ago. And so the water's moving swiftly here where there's a big depth, and underneath this water surface there's just the bare earth. But in this section where the water's moving relatively slowly around these obstructions. In part, it's moving slowly because it's shallow, but also it's moving slowly because there's park bench and there's children's playground equipment and trees and trash cans. There's just all sorts of debris in the way. And it's hard to see, but here at the back is where they had the gates. This is where you can normally drive into the park, and they had a few slats of the gate installed. So the river was high a year ago, and if we needed to calculate the composite N value, Manning's N, the Horton-Einstein method is in our book, and what it suggests is that what you can do is take the average N value and weight it based on the perimeter. And so what you'd do is you'd find the overall wetted perimeter, so the length of distance from the side, the bottom length, the side slopes of the main channel, the bottom of the main channel, and then all of those same things on the right bank. So you'd find the overall total perimeter distance, and then you would weight the N value by multiplying each segment by the applicable perimeter distance. And so, if you had, this was just a grassy hillside, you'd find the N value for that grassy hillside and you'd multiply it by whatever this segment length is. And then if this section of the floodplain is a bunch of tree stumps and vegetation and cattails and so on, you'd find the applicable end value and multiply it by the end value for that section. And then you do the same thing here. Maybe it has riprap on this side of the main channel, natural soil at the bottom. And so this formula is just a way of finding out the composite end value if you're going to try and calculate the flow capacity of the overall channel. Then you'd need to find out the applicable end value, which end value to use, because it's going to be different types of material at each section. There's other approaches. Sometimes what they might do is calculate just in completely separate segments. So rather than doing the whole channel and finding the composite end value, you might just find out what's the capacity of the main channel, what's the capacity of the left floodplain bank, the right floodplain bank, and so on. But our book does have this Horton-Einstein method described. Now, remember, for Manning's equation, if we are going to combine together the two areas that are in the numerator of Manning's equation, that takes it to the 5/3 power, and then the wetted perimeter to the 2/3 power. Channel capacity can be maximized by minimizing the wetted perimeter. So let's say that we have a fixed slope, and that's usually not something we can change. Engineers get to play with some parameters, like we could change what the channel is lined with. Like we could put concrete lining at the bottom of a stream, or we could just make it grassy. What we can't usually do is change the ground slope. Not over a long distance. Over a short distance you can, but between Pittsburgh and Cincinnati there's just a certain elevation change, and so we can't change the slope. There's a place the water's going to go, there's a length of the flow path, there's an elevation difference, and so slope is fixed. Let's say that the end value is fixed, or that we know what it is at least. And the flow area is determined by, in a lot of cases, where is the land available to put a channel. You may have houses on either side of an irrigation canal that can't be relocated, so you know what the cross-sectional area is. But as I've already mentioned, the way that you maximize flow rate to try and get as much flow through a channel as possible is by minimizing the wetted perimeter. So let me just let's compare and contrast these different channels. They all have one thing in common. You can see that they all have a cross-sectional area of 20 meters squared. So this one is a deep, narrow channel. Think about, why would there not be as much flow capacity for this as there would for this channel? Like, even before you put it into the formula, like if you're just thinking about it logically, you know that the surface applies resistance to the flow. And so here, in this channel that's on the far left, there's a lot of contact with a surface that's not moving and is applying resistance. So the overall length of wetted perimeter is big relative to the flow area, so there's going to be a lot of resistance. Whereas here, in the one that's 4 by 5, this section that's in the middle is pretty far away from any of these edges where the shear stress is applied. So here in the middle, it's a little bit, you could say, insulated, or it's free from the effects of shear stress, whereas there isn't much area in this section that's far away from those surfaces that's applying the resistive force. So let's do a spreadsheet example where we just compare these different areas and look at how the flow rate is affected. This isn't something that you necessarily have to do, although you can if you like. I'm just going to copy this slide so that I can paste it into the spreadsheet, and we'll use it as a reference. All right. So we've got a rectangular channel, and we know that the slope is 0.01 and the end value is 0.013. And we're going to take a look at several different bottom widths, B. So B, remember, lowercase b means the bottom width of a channel. We're going to play around with different flow depths, Y. We'll calculate the area from that, the wetted perimeter from that, the hydraulic radius, and then we'll calculate the flow rate. I guess we don't even need the hydraulic radius if we're going to just use this version of Manning's equation. I'll just omit that entirely. Q. All right, so there's a 2 meter width, there's a 10 meter width, there was one that's 5 and 4. Okay, so we had a depth of 10, a depth of 2, a depth of 4, and a depth of 5. So each of these is going to have the same area. You'd see it's 20 meters squared for all of them. So they share a common area, but they're not going to have the same flow capacity. Even though it's the same area, and the same slope, and it's made out of the same material, the wetted perimeter will be different. So the wetted perimeter is 2 times the depth plus the bottom width. That's the formula for the wetted perimeter for a rectangular channel. So 2 times the depth is because it's the 10 meters on the left, the 10 meters on the right, and the bottom width. So that's why we get 22 is the wetted perimeter for this first narrow, deep section. And I think we'll see that it has the worst flow rate capacity. So Q here, I'm going to do, it is the area to the 5/3, to the power of 5/3, times the slope to the 1/2, and then divide it by the roughness value times the wetted perimeter to the power of 2/3. So I'll just type in 0.66667 for that. All right, so the flow capacity here, by the way, I should have written units, cubic meters per second. So 144 cubic meters per second is what we could convey with this narrow, deep channel. But for a channel that is shallow and wide, the flow capacity is way better because it's got so much less wetted perimeter. Even though it's the same dimensions, 2 by 10, there's only 14 meters of wetted perimeter instead of 22. So there's just less length of concrete in contact with the water. So more flow capacity. This can continue downward. We can see that the channel that's 4 by 5 of all of these had the least wetted perimeter. So it's going to be the one that has the highest flow capacity of these 4 options. So minimize the wetted perimeter and maximize the flow capacity. That's the lesson that we learn. What's ideal though? Like what's the best, the most efficient cross section? That's the question. And for a rectangular shape, the most efficient is a half square. So what we would want to do is we would want to have it so that the well, I'll show you the most efficient formulas in a moment. Let's see, let me go to that. So a half square is the most efficient rectangular shape, and so it's going to have an area of 2y squared, a wetted perimeter of 4y, and then a b. If it's rectangular, the top and the bottom width are the same, are 2y. So let me just show you here. If we had a depth that was 3.1623, and a B, what did it say the B needs to be? 2 times y. Okay, so 2 times that. It's like I've forgotten how to do formulas. Equals 2 times that. All right. The area would be the depth times the width. So we'll see it's still 20.00026. Okay, the wetted perimeter for a rectangular is still going to be the width plus twice the depth. So I can continue that formula downward. It's slightly less than this one was, and so the flow capacity, the most that we could convey for some channel with the area of 20 would be 208 cubic meters per second. So there are a variety of different shapes that are the most efficient channel shapes. For a trapezoid, for example, the best trapezoid is one that most closely resembles a quarter circle. So you can see here that the trapezoid that most closely resembles a quarter circle is the one that has a side slope angle t, where t is the horizontal component with 1 unit of vertical. So square root of 3 divided by 3, it's less than 1. So it's a pretty steep side slope to get the best trapezoidal channel. But for some certain depth, we could find the wetted perimeter and the bottom width and the cross-sectional area for that applicable depth to find the best trapezoidal channel that's going to have the most flow capacity. Interestingly, the hydraulic radius for the best trapezoidal channel is just the depth divided by 2. So we know, for example, a triangular, the best triangular channel is the one that most closely resembles a quarter circle. So the one that maximizes the flow area while minimizing the wetted perimeter. So what will be the flow depth in the best triangular cross-section for 2.5 cubic meters per second, an n value of 0.013, and a slope of 0.01. So if we're going to use Manning's equation here, and we know what flow rate we have to achieve, and we know what this material is made out of here, the 0.013 is most likely a concrete, and we want to determine the best flow depth, we're basically going to substitute in for the area y squared. So let's do this on the board. Starting with Manning's equation, Q is area to the 5/3, slope to the 1/2, divided by n times wetted perimeter to the 2/3. Okay, so if it's a triangular shape, then we're just going to have y squared to the 5/3 power. And then the slope here, 0.01 to the power of 1/2 is divided by n, so 0.013, and then multiply that by the wetted perimeter, which is, for a triangle, 2.83 times y to the power of 2/3, and then we're setting this equal to the flow rate, 2.5 cubic meters per second. So solve for y. You can do it with the calculator. We can try it on Excel. Let's just start a new sheet here. Okay, so I'm going to have a guess value of y. So if the depth is 1 meter, then what is the flow rate that we get out of that? Okay, so here I'll type in, it is y squared And then, boy, and then I have to take that to the power of 5/3. Times the slope to the 1/2, so that was 0.01 to the power of 0.5, divided by 0.013 times 2.83 times y, and then that's to the power of 2/3. Well, I need to be careful though, because it's the 2/3 does not include the n value. It's just 2.83 times the depth. There we go. So if you're doing it on your calculator, hopefully we'll get the same thing. So for a depth of 1, that would give us a flow rate of 2.5. So what we want to see is what depth gives us a flow rate of 2.5. That's the target flow rate that this example is asking about. So we could change using goal seek. Set the flow rate to 2.5 by changing the depth. And then we say, all right. And it finds that a depth of 0.85 meters is what depth would give us that flow rate of 2.5 cubic meters per second. Did anybody solve this with their calculator? And did you also get 0.85? All right, good. All right, so that's what we mean by the most efficient. The most efficient channel is the one that has the shape that maximizes the flow capacity for a certain depth. All right, lastly, let's do another Manning's equation, trapezoidal channel, unknown depth problem. I think by now you're probably getting the sense that these are important. The number of these that we've solved in class and the ones that you get in the homework. So this has a bottom width, lowercase b, of 2 meters. It's grassy, so our n value is 0.035, trapezoidal channel. 1-to-1 side slopes means that t is 1, and we want to accommodate a flow rate of 21 cubic meters per second. So for a bed slope of 0.35%, what will be the depth? Okay, so I'm going to pause, and if you've got that extra calculator that just has Manning's equation programmed into it, this will be an easy one for you. Otherwise, you may need to put Manning's equation back into your calculator again, or you can use your spreadsheet if you want to do it that way. But let's see if you can solve for y. What is the normal depth, assuming steady uniform flow? All right, so remember that the numerical procedure here is that we have to guess what the depth might be and find out what's the area and wetted perimeter from that. And then on the left-hand side of the equation, we're going to have all of our known parameters that aren't changing. Well, here is how we've rearranged it. So let me paste that. I guess I'll put all of the known stuff on the right-hand side and the unknown stuff based on the depth on the left-hand side. So left-hand side is going to be area to the power of 5/3 divided by the wetted perimeter to the power of 2/3. So this left-hand side is if the depth is 1. On the right-hand side is where I have all the known parameters that aren't changing as a function of depth. So n value times the flow rate divided by the slope to the 1/2 power. So you can see that they don't equal each other right now, so we're going to have a difference that we want to have minimized down to 0. So to minimize it down to 0, my guess of 1 is too small. What if it was 1.1? Getting closer, 1.2. Yes, getting closer, 1.5. So at this point, I'll just go ahead and automate the guess process with goal-seek. And the objective here is that we want the difference to be 0, and it can change the depth in order to achieve that difference of 0. So click OK. Yeah, 2.03. I'd done my calculations on paper rounding W down to 1.414. And I guess those extra decimals make a difference when you're taking it to the 5/3 power. So this is our flow depth, 2.03 meters. By now, I think probably you're getting pretty good at solving for the unknown flow depth in a trapezoidal channel with Manning's equation. I don't know that we'll have any more of those. Just before we part ways for the weekend, a reminder that on Monday at 1 is when you'll upload your demand estimation, and then on Friday by 1 is when you'll upload the assignment having to do with this stuff from Chapter 8 we've been working on. No, not Chapter 8. Chapter 11. It's homework 8. All right. That's it for today. Take care.